Okay, let's get going. There's actually a clock now in the room. I don't know if you've noticed this. It's not very helpful to you guys, but it sure is helpful to me. They used to have the clock just sitting right over here by the printer, and it was kind of behind the printer, so no one could really see it except for me as well. So clock placement in this room is not necessarily the best. Today we will continue in Chapter 2, and hopefully we will discuss project number 1. And also we'll spend a little bit of time reviewing some of the stuff that we did last time, just to make sure things were clear. If I don't get to project number 1 today, I do want to mention 2 things about it. First of all, you can work in groups of up to size 2, so you can work in pairs. And as also, the project is due Thursday, September 13th at class time. And that's subject to change depending upon how far we get. Basically, we need to get through all of Chapter 2, Part 1, and I think we will before the project due date. Okay. Are there any questions before we get going here? So, just to review, what we have in our class, we have this random variable y, and it's distributed f. What f is going to mean for us in a parametric bootstrap setting that we're talking about right now would be perhaps, f might be normal mu sigma squared. Now in a parametric bootstrap setting then, for our f hat, we need to pick it. And it would make sense if you know or you think that a normal distribution works for the population itself. It makes sense then that you would use, let's say, a normal distribution here and replace the corresponding parameters with estimates that make sense. So mu hat, let's say it's sample mean, sigma hat squared. How about we use the unbiased sample variance rather than, of course, the bias sample variance, like the maximum likelihood estimate. So that that would make sense to use that. And then we can say that y star then is distributed f hat. Now we're going to be interested in estimating some quantity about the population, which we denote by theta. Theta could be just as simple as mu or sigma squared, or some function of mu and sigma squared, maybe a coefficient of variation, or maybe simply like a probability associated with f. And what we're going to do is choose a statistic, t, that's going to estimate theta. And of course this estimate, or estimator, is not going to be perfect. And we would like to take into account the variation of t when we try to estimate theta. So how do we do that? Well, we need the distribution of t, or sampling distribution, you could say. And we denote that by a g. So t is distributed g. Now in a parametric setting, oftentimes you're going to be able to simply derive what t is. I'm sorry, what g is. But there are other settings where it might be difficult to find exactly what g is. So what we can do is think in terms of the bootstrap world and look at t star itself, which uses then f hat to come up with the distribution for t star, which we denote by g hat. G hat estimates g. Once we have g hat, then we can use g hat instead of g for inferences like confidence intervals and hypothesis tests. So that's why we're really interested in g. And the bootstrap provides us a way to do that. Now, there are actually 2 different ways that we can get g hat. So, how do we get g hat? Method number 1. I'll just derive it. Okay? And that will give you g hat exactly. But there may be times where the math behind it's, quite complicated. Maybe it's just intractable, depending upon t. So, An alternative is basically Monte Carlo simulation. And from that, you're going to get a G hat with, let's say, a subscript R, or capital R. That corresponds to how many replicates you do in your simulation. And we call this simulation resampling. And since we have an actual distribution that we're starting with here, it's parametric resampling, or parametric bootstrap. Okay, so that sets the stage for then what we're talking about right now with respect to the bootstrap. Do note that I mentioned how we really want this G hat, so eventually we can do some inferences. It's going to take us a while before we can actually do inferences. I have written down here page 255 in the notes is the first time that we're actually going to do like confidence intervals. So please be patient. It just takes some time to build up to it. Okay. So then that takes us to where we left off on page 211 in the notes. Okay, so we were talking about an example dealing with a normal distribution last time, and that's one reason why I chose a normal distribution here. So what we're going to be interested in is, again, eventually working in this setting here, we're going to use Monte Carlo simulation. And to make things simple for us, so that we can do some stuff with R, how about we say that F is normal 0, 1. Okay? Now we're going to take a sample from it. Sample size 100. So let's take a sample from a normal distribution. Simply use the rnorm function. I'm going to set a seed to make sure that I can reproduce my results at a later time. And so y1 is 0.813, y2 is negative 2.12, and so on. Now, if you didn't necessarily know that it came from a normal distribution, what would you do first? Well, let's actually do a histogram, do maybe an EDF plot, and compare the normal distribution to the actual sample, these actual plots. So similar to what we've done before. I don't know if I've actually used this argument before. Sorry if I haven't mentioned this before. MF row, does anyone know what that means?
How many rows are you going to have in your graphics window?
Yeah, my plot. So par is a great little function. R stands for graphics parameters. And I'm going to make frame by row, 1 row, 2 columns worth of plots. This LEND argument here is another just option in your graphics. And I think, at least we've used it before. I don't know if I might have actually accidentally skipped over it. What that just corresponds to is just what the, when you're drawing lines, what do they look like at the end? I want them to square them off. I think the default is to have them rounded a little bit. If you take that off, that argument, you will see the effects on this EDF. And that's a way to learn, I guess you could say, what these arguments mean. So we've already looked at how to do histograms before. We've already looked at how to plot curves on top of histograms. So I'm just going to do that. I'm going to actually plot my standard normal distribution, and you get what you would expect if you are actually sampling from a normal distribution. And then I'm going to do EDF plots, similar to what we did before. And I'm going to plot a curve on it. That's the actual standard normal distribution. So the CDF of the standard normal. And again, we get what we would basically expect. Okay? So, sometimes people get a little bit picky about, well, geez, we don't see this black line. This is the EDF falling right on top of that red line, which is the standard normal. Well, you're not going to get that exactly. There's going to be some variability. So this is a case where indeed normal 0, 1 is correct, and we see that we have some deviation from it. Even on this histogram, look at this bar is a little bit higher than the line. Okay. So let's move on. So in this particular setting, for what we did last time, now we're on page 213. we're going to use a parametric bootstrap. So y star itself is going to be distributed normal x bar sigma hat squared. Sigma hat squared is the unbiased estimator of the variance. So first I'm going to find the mean. I'm going to put that as t. We're going to be interested in the mean itself, so that's what I'm letting t be, the sample mean. And as the sample size, I'm going to take 1,000 resamples, set as C so I can reproduce the results. Okay. Now to actually do the resampling, there are two ways we can do it. I'm going to use one way right now, and then I'll show you later on today how to use what's called a boot function. When you're doing a parametric bootstrap, it's often easier not to use the boot function. So that's why I'm doing it this way. So what I'm going to do is create a matrix that contains my resample data values. And the first argument of the matrix is data. What am I going to put in the cells in the matrix? I'm going to simulate from a normal distribution. My sample size originally was n. I'm going to take r resamples. So that's why I'm going to have n times r different values. My mean is the sample mean from my original sample. The standard deviation is the original standard deviation, or the standard deviation from the original sample. Number of rows to the matrix, capital R, number of columns, capital N. I'm sorry, not capital. Just N. So I put that into an object called y.star, and I look at the first 5 resamples. And there we go. So notice, some of you, for example, in that day number 1 quiz, you might have actually, let's say, done a for loop where you would have done 1 resample at a time. Well, there's no reason to do that if you're just simply using, a random number generation tool such as RNorm. Just simulate everything at the same time. Okay. So this negative 1.22 then would be, let's say, y1 star. 0.9 is y2 star. If you want to actually specify the actual resample number, you would say that this is y11 star, this is y12 star, y13 star, and so on. Just to emphasize the point, notice that these data values that you see here are not the same as what was in y, because we are resampling from a parametric distribution. Just for emphasis. Okay. Now, how do I find now my t-stars? Similar to what we did in the Chapter 1 notes. I'm going to use the apply function. I'm going to apply to everything that's in y star by row the function mean. Put that into t dot star, summarize it, and there's a summary of what we get. Well, let's do some plots of these t-stars. Or if you want to, you could actually look at the first 6 of these t-stars using the head function. So negative 0.2245 is t star 1, and that's the mean of this first row. Continuing down here that we have on these samples. We can again do a histogram for my curve to plot then the normal distribution on it. In other words, sorry, I'm getting ahead of myself here. Okay, I want to see the distribution of t star now that I have these resamples. And so what I'm going to do is visualize it one way through a histogram. And we know what t star actually is. What is it? Normal mean of t, or y bar, with a variance of sigma hat squared divided by n. So we're sampling from a normal distribution. I mean, we know that from Site 882. So I use the curve function to look at that, and hopefully they agree. And they largely do. I'm going to also do an EDF plot as well. And we see how that red line, which is the true distribution for t star, my g hat, we see how close that is to the black, the EDF. So corresponding to what we were talking about here, basically what I've just shown you now on those two plots, I've shown you what G hat is, and I've shown you what G hat R is on those two plots. We can also now look at expected values. So, for example, red pen. The expected value of T star given F hat, well, that's just Y bar, right? We know the distribution of G hat. The approximate value using Monte Carlo simulation, or in other words, what we call resampling in our class, is just simply 1 over 1,000 times the sum of all these T stars. And you get negative 0.05033. What was Y bar exactly? Negative 0.049. So we can see how we're quite close, which would be expected from the law of large numbers. For emphasis, as I started mentioning last time, our book uses basically two sets of notation to mean this expected value. Expected value T star given F hat, but also they'll use this little shorter notation, expected value star of T star, to mean this as well. Just make sure you understand that. Okay, some questions then. First one's quite easy. Why do we resample with replacement from the original data in the Chapter 1 example, but we are not resampling this way here? Well, we know what the parametric distribution is. That's why. It's a parametric bootstrap rather than non-parametric. And then second here, the variance of T star given F hat. What is that? What is its value? We've already basically given it. Sigma hat squared divided by n. Okay. How would we use Monte Carlo simulation to estimate it? I'll talk more about this later, but this is a good time to bring it up now. How would we use Monte Carlo simulation to estimate it? Or how would we use the resamples to estimate it?
Standard deviation of the samples.
Var T star. There you go. 0.0083. And let's see, what was the actual value? Look how close they are. There is the true value. So what I've given you here is 3 variances. The last one is the variance of T, because we know what the distribution is for F. This is the variance of T, sigma squared divided by n. Then, using the bootstrap, the variance star of T star, or the variance of T star given F hat, is 0.0087. Through using Monte Carlo simulation, then, the estimate of the variance star of T star is 0.0083. Now again, this is just meant to be a simple example where we have things that we're familiar with and that we can compare to, just to kind of, you could say, proof by example that this bootstrap is working. Okay. We can go a little bit to a more complicated example that has some more real-life application by taking a look at this Chapter 2 extra set of notes. So this is comes from a project that I gave my students last time I taught this course in spring 2010. Now, obviously, wind power is something that's very important nowadays. And if you go to JSM, you typically now see some kind of presentations always on wind power and how we can model it. This is a simple way to model it that I have found in the non-statistical literature, and that is they use simply probability distributions to understand the distribution of wind speeds, because they need to know that for, let's say, particular locations to estimate how much power might be generated from a wind turbine. And one simple distribution that they use to model that's what's called the Rayleigh distribution. If you want a Castellan-Berger reference, this is on page 131 of Castellan-Berger. We'll talk about this distribution there. Perhaps some of you have had homework problems on this distribution before. Anyway, so there's just a little paper that talks about it. And using that as motivation, then, what I did a few years ago was I searched on the internet for some historic wind data for Lincoln. And I focused just on February's. And from 2000 to 2004, these are the winds, the average daily wind speeds. I don't know how they actually calculate average daily wind speeds. Maybe every hour they find what the wind speed is and take an average of it. I couldn't find exactly how they calculated that. But for example, on February 1 of 2004, the average daily wind speed was 9.4. On February 2 was 12.7, and so on. And so you can see that we have a sample size 142. Okay. And what I would like to do is use the Rayleigh distribution with this data. You notice with the Rayleigh distribution here, there is one parameter, beta. And what you want to do if you have a parameter? Estimate it. Find its distribution. Do some inferences about what the true value of beta is. You can maybe put it into the context of, let's say particular companies trying to decide, well, should they put a wind turbine here, or wind turbine there. And so what they might want to do is collect some data for particular locations for wind speed, and and estimate what the betas would be. Depending upon what those betas will be, they can determine, well, this location might be better than another. That's maybe not overly simplified example. That's what I would imagine that they could do with this kind of stuff. And the Rayleigh distribution is actually a special case of a Weibull, which all of you should have at least a little experience with. And in R's parameterization, the parameter A for the Weibull will be 2, and B, beta times the square root of 2. I'm not going to throw up the Weibull distribution because it's not important for what we're going to do. But in order to actually do some resampling, we need to use the R Weibull function, and we need to know what this is in the context of the Weibull. Okay. Now, you may be thinking here, well, I'm going to assume that I have IID data. What do you think? Do you think this is IID? No. Okay. Why? Well, you might think that, what happens on the first is going to be related to what happens on the second, and so on. So, let's say you want to find a maximum likely estimate. What do? Well, you take the product of a whole bunch of PDFs, assuming that each of the x's are independent, or at least that's what you would learn at 883. Do I have independent observations here? Looking at it, or without looking too further, I would say no. Maybe we could use, for example, some time series methods to help better understand the data over time. But what I typically have seen in the little bit of literature search that I've done is that independence is assumed. I looked into it further, though. I found the autocorrelations for every year. Does anyone know what an autocorrelation is?
Essentially the relationship
from one time period to another. So, in other words, I looked, for example, what is the correlation between, let's say, time point t and time point t minus 1. And what I found is that basically the autocorrelations are pretty much all non-significant. Not just the first autocorrelation, but second, third, and so on. Except for one autocorrelation 2002. Well, I'm not going to let that rain on my parade, and I'm still going to use this data set, assuming everything's independent. Well, what's the maximum likelihood estimate then in this setting? Well, let me get a red pen. You could derive it, and you would find it's the sum of kx squared divided by 2n. It's not too hard to derive it. And also, don't forget the square root there. So that's the maximum likelihood estimate. And what I'm going to be interested in is looking at using the bootstrap to work with this beta. So my theta is going to be beta. Here's my t. What do I need? I need the distribution of t. Now, we've talked about the first day of class, why it's important to get the sampling distribution. There were 3 ways to do that. One way would be to derive it, just simply derive it. Find that distribution of t. You know the x's are Rayleigh. What would you do then? (882). What would you do? Let's break it up into components. Suppose I want to know the distribution of x squared. What would you do? Take the problem to your 882 teacher and say, I don't remember how to do this. Could you help me out? I think you wouldn't get a very good look from that teacher. Well, do some kind of transformation. Let's let y be equal to x squared. Get to the Jacobian. Do all that fun stuff. You got it. Okay? Well, how about then finding this? Well, you could go about doing the same kind of technique. Get the distribution of 2 of the x's squared. Why don't you just then extend it to the n-dimensional case, right? So now we have the distribution of that. It's not too hard. How about we just call this w? And so now what you need then is the distribution of w divided by 2n. Well, again, 882. There you go. I did not do that here. It just doesn't look like fun. Instead, what you could do, so that's method number 1. Method number 2 to get at the sampling distribution for t is to use asymptotics. So you could use stuff that you learn in 980 to do this. I assume just you 3 have taken 980? I'm sorry. Anybody else taken 980? Okay. So I'm going to look at you guys here. Did you talk about the asymptotic, how to prove the asymptotic normality of a maximum likelihood estimate?
We barely got to proving this in Jordan.
Okay. Well, then we'll talk about what you would have learned in Castellenberg. Okay. In Castellenberg, did I put a page reference? I think it's in my note. Yeah. So.
Castellenberg 472.
Yeah. Now, at least all of you in your classes, you've heard the following. Maximum likelihood estimators are asymptotically normal. Or in other words, for a large sample, they have a normal distribution. Where the maximum likelihood estimate is a consistent estimator of the parameter. Or in other words, as n gets large, beta hat gets closer and closer to beta. And what about the variance? What did you learn? Without looking at my note. The variance is 1 over Fisher's information squared. Oh, I'm sorry, not squared. Oh my gosh, no. Ah, embarrassing. Fortunately. No, it's 1 over Fisher information. No, I don't know why I want to say square. Let me just double check here. What page was it again? 472. 1 over Fisher information. You might remember there's 2 definitions of Fisher information. One works with the squared and one doesn't. That's what I was going to use. Anyway, so 1 over the Fisher information. And so with that then, you could say that T has an approximate distribution of, for large sample, normal beta with a variance of beta squared divided by 4n. Go through the Fisher information derivation on your own. I won't at least ask you that on a test, maybe for a project, just so that you get a reminder of what was in the sum burner. Of course, you don't know what beta is, so how you gonna use this distribution? Well, you put hats on top of the betas. In a 980 setting, you would have said something along these lines instead. Square root of n times t minus beta converges in distribution to a normal random variable with mean 0 and variance beta squared divided by 4. Okay, so that's method number 2. Method number 3 then is to use the bootstrap. We're going to compare the asymptotic approximation to the bootstrap. And again, the reason why we do that is to compare what we're doing now to something that's at least somewhat familiar to you. Okay, so the first thing that we want to do is read in the data. It's a comma delimited file, so that's why I have an SEP quote, comma, quote right there in my read.table statement. I put into an object called wind. I pull the wind speeds out. I put it into an object called x. Find my sample size, find my maximum likelihood estimate. 7.87. You can delete this particular line there in the notes. So just like what we did in the last example, you want to determine, well, I have some real data here. Is a Rayleigh distribution appropriate? So I do an EDF. I do a QQ plot as well. I'll talk more about QQ plot in a little bit. But for the EDF, for my curve here, my curve function, what am I going to do? I'm going to use the p-Weibull function, because there isn't a p-Rayleigh function out there. Shape equal to scale equal beta hat times the square root of 2. The reason why I'm using that is because we don't know what beta is, and you would think that using the maximum likelihood estimate, we're going to get the closest agreement if there is an agreement between the two. So here's my EDF. What do you think? Yeah, it's not too bad. So you come home tonight and have dinner, talk to your kids or talk to your significant other, and they ask them, what did you learn today? Well, I learned that Lincoln has a Rayleigh distribution for its wind speeds in February. Okay. QQ plot. How do you interpret a QQ plot? QQ plot, quantile plot. So what do we look at?
If your
How the dots
observed quantiles line up on the
Then
line,
you're good to go. Yeah. So if the points lie on that straight line there, that suggests that the distribution that you picked is reasonable, and it looks it's pretty close. Again, you shouldn't expect perfection. How do we do a QQ plot here? Let's talk about that. There's a variety of different ways to do it, so that's why I want to actually talk about it here. This is a way that our book, I shouldn't say our book does it. I think this is the best way to do a QQ plot. And you'll see my code coming up. So, a QQ plot, quantile plot. So on the y-axis, we want quantiles from our observed data. Well, what do I mean by quantiles? Well, these are simply the order statistics. Okay? And we're going to plot them against the quantiles from some other kind of distribution. Here it's going to be Rayleigh. So let's let Q sub alpha, let's say, be the alpha quantile from a Rayleigh distribution. The thing, though, is that I need to decide, well, what should alpha be for y1? What should alpha be for yn? This is where different definitions of a QQ plot arise. This is what I use. Basically, it's motivated from what the book does, but the book sometimes does it slightly different. In the end, it's going to only make small differences on your plots. So this is what I use. So let me actually create a table. Let's see. Y, how should I do this? Do J, we'll do alpha, and so J is going to represent the ordered value. So this is J equal 1, J equal 1. So for J equal 1, I'm going to use 1 over n plus 1. For J equal 2, I'm going to use 2 over n plus 2. Oh, sorry, n plus 1. I'm going to keep on going down to the nth value. I'm going to use n over n plus 1. So in other words, I'm going to go to my Rayleigh distribution, find the 1 over n plus 1 quantile, and I'm going to plot that against my smallest value. Now, why do you think I chose n plus 1 in this denominator rather than n?
So you don't get the 100.
So
you don't get the 100th quantile?
Yeah. So, if I chose 1 over n, look what happens. 1. It's the very last value. So, what's the 1.0 quantile from a Rayleigh distribution? Now, the Rayleigh distribution, let's take a look. You know what? Shoot, we haven't actually looked at a plot of it. Well, you can see a plot on page 4. Okay? Notice it's a right skewed distribution. So what do you think the 1.0 quantile from a Rayleigh distribution would be? Infinity. Okay. So that's the problem. So that's why one definition then of doing these kinds of QQ plots is to make that little +1 adjustment. Okay? So to do the plot then, so we'll be doing a lot of QQ plots throughout the semester, so that's why I want to take time to talk about this. I need to find my quantiles. And so what I'm going to do is create an object called Rayleigh.quant. I'm going to use the qwibal function. And then for the p argument, I'm going to take a sequence of numbers from 1 over n plus 1 to 1 minus 1 over n plus 1, or I could just say n over n plus 1, by 1 over n plus 1. And then use the appropriate shape and scale parameters in the context of a Weibel distribution for a Rayleigh. Then I used simply the plot function where I sort for my y-axis values x. So I need y, I need the first order statistic, the second order statistic, and so on. Plot that versus the quantiles, and this is the plot that I get. And as we said earlier, yeah, seems reasonable. Great. Something that's maybe often more easier to look at, but does not necessarily always give the best picture, is using a histogram. So we could use a histogram of the data. I use the curve function to do the distribution of the Rayleigh. And I do two different forms of the histogram. All I do is I change the number of classes using the breaks function. That's what breaks I make, and this is what we get. So, it seems to roughly follow a Rayleigh distribution. Again, it's not perfect. And, when looking at this plot here, you might think it's not as good as maybe what we were seeing with EDF. And that's somewhat of a problem that you have with looking at histograms and distributions plotted over it, is that, you can change the width of the classes. That could, change your judgment. And just the fact that you even have classes overall. But, roughly speaking, it looks reasonable. Okay, so now that we're satisfied with the Rayleigh distribution, then what we can do is use the Rayleigh distribution as our f hat. So our f hat in this particular case would be the Rayleigh beta hat. And what I'm going to be interested in is doing some stuff involving my maximum likelihood estimate, t, which is our beta hat. So I want to estimate that sampling distribution. I'm going to use 1,999 resamples. You'll see why later today, hopefully, why I'm using that versus 2,000 resamples. I'm going to set a C so I can reproduce my results. And then I just kind of replicate a lot of the code that we saw before, where I'm going to find all my X stars using now the R-Weibull function. Notice the number of observations. I'm sorry, well, I guess you can say the number of observations. N times capital R. I put that all into a matrix. So in the last example, I put this whole, equivalently, I put this whole R-Weibull code right there. I just ended up breaking them up. And so that X1 star is 5.06, X2 star is 7.78, and so on. Now what I need to do is find the maximum likelihood estimate for every single resample, all 1,999 of them. So I write a function to help me do that. I say the function is called find.mle. I say function of x. So I'm going to pass in my data. I'm going to find the number of observations, and then simply square root of the sum of the x's squared divided by 2n. That's what's returned to me, so that the actual maximum likelihood estimate on the original data is 7.87. Now let's do it with the resamples. So I say apply to my matrix of resamples by row, function I want to apply every single time, find.mle, and here we go. So T1 star, T2 star, and so on. I can then estimate the distribution of T star through these resamples by looking at a histogram, by also looking at an EDF plot. If I want, I can also find expected values, just like what we did in the previous example. Now the curve function that I use here, notice what's being plotted, normal. What I chose to plot was the asymptotic distribution that I showed you at the beginning. So method number 2 to approximate the distribution of T. So look at the mean, beta hat, the standard deviation, beta hat divided by quantity 2 times the square root of n. So just the asymptotic distribution. And look at it. Look how it follows basically what we got from the bootstrap. So again, the purpose here is to show you now in a little bit more less familiar example how the bootstrap is going to give you the same thing as the asymptotic distribution practically. So again, we would use now the distribution here, either bootstrap or asymptotic, to do various different stuff. So for example, you know how to do a walled confidence interval for beta. Okay, so take beta hat plus or minus the quantile from the standard normal times that square root of the variance. Well, we're going to learn, not today, but probably next week, how you could use now this bootstrap distribution that we have here, how we can use that to find a confidence interval as well. And you didn't need to take set 980, and in fact, actually, you need to take set 883 to apply the bootstrap, if you wanted to. Where if you wanted to really understand how this stuff works in terms of asymptotics, well, you need to take 980.
I have a quick question. With the par statement, I see that you set it up there again. Do you have to set that up each time you graph, or is it something that once it's established, it continues that format?
Yeah, well, once it's set, you don't need to set it again.
Okay.
You know, maybe I set it more than what I needed to in this particular example. And I noticed one little option here, at least we have to discuss here, but maybe some of you have run into it elsewhere. This PTY stands for plot type. The default is M, which basically says once you maximize the area from which the actual plot itself is covering in terms of the plot window, S says make it square. And sometimes, especially when you are doing a QQ plot, it's nice to have it be squared. Although it would have been nice to put that on exactly, or I guess that's not a QQ plot, but one that we had earlier, would be nice to put it always, the QQ plot on the same scale as well for X and Y axis. And unfortunately, did not do that. Shame on me. But let's, even talk about a little bit more of a complicated example. We'll talk about this number 4 later. But let's say that we were interested in this statistic instead for T. What would you use this statistic for? Does it look familiar? Likelihood ratio test. So we know that for a large sample, this converges in distribution to a chi-square, whatever degrees of freedom are, depending upon what you're testing. Let's say I wanted to test beta is equal to some number, we'll call it beta 0, versus beta does not equal beta 0. In that case, I would have a chi-square 1. This is for a large sample. And we generally have a large sample here, but maybe if you had a smaller sample size, could you trust that? Maybe not. So what could you do? Well, you could use the parametric bootstrap instead. Use the bootstrap to try to estimate that distribution of T by taking resamples. Again, starting from the Rayleigh distribution, forming T every single time, we call it T star, and there you get your distribution. This is foreshadowing a little bit something that we're going to do in chapter 4 here. But when you do a hypothesis test, what's an assumption that you make when you are interested in the sampling distribution of your test statistic? Assume the null is true. Okay. How would you resample assuming the null is true? Would you still use a Rayleigh with beta hat? No. You have to make a change. Now you're going to need to resample using beta 0. So that's foreshadowing stuff that we'll do in chapter 4. Okay. Any questions? Is there a question? Okay. So that takes us then to page 215. Okay, let me just take a quick look here. So, I don't need to mention this, but a great way to learn a topic from a course is to actually try to reproduce the examples that are in the book. And so one thing that I've done here, more so than in other classes that I've done, or that I've taught if you haven't been before, is to reproduce the examples. So you can see here the program name, example 2.4 underscore 2.5 underscore 2.6 underscore, and so on. And so we'll be talking about this data a lot. And this is what's called the air conditioning data in the book. And if you don't have your book with you today, fortunately I have this here in the notes. What we have here is just simply some failure times. So this is something that you would see like in the survival analysis class or the reliability analysis class. And we have failure times of air conditioners on airplanes. So 3 hours, 5 hours, those poor people on the airplane, 487 hours. And when you're working with failure data like this, a very common distribution that's used is a simple exponential distribution. So this is what the exponential CDF looks like in the definition of our book. The actual density function would look like this. This is the equivalent definition to what Cassell and Berger does, except for they use a lambda instead of a mu. Remember, for an exponential distribution, expected value of y is equal to mu. The variance of y is equal to mu squared. And one of the first things that they do with this data, and we'll look at how to reproduce this result shortly, is that they do, an EDF plot with then the curve there is the exponential distribution using mu equal y bar, sample mean, and they also look at then a QQ plot as well. So we only have a sample size of 12 here. What do you think about the exponential distribution? Maybe it's not bad. I mean, you might be worried about that point there, because it's far from the line. But, again, you only have a sample size of 12. You are trying to, in that case, estimate an extreme quantile from a right-skewed distribution using a sample size of 12. You're typically not going to do a good job. So if I see something like this, I wouldn't normally get too worried about it. Note that R, unfortunately, has a different parameterization for the exponential. Instead of using 1 over mu out in front, it uses just simply lambda. And so look what happens up in the power for the E there. You also have just lambda. So we need to know that because we are going to need to take resamples eventually using the corresponding function at R. So I'm going to go through this fast because this is basically just the same kind of code that we've been talking about. I put my data into R. I find T, my sample mean. We're going to be interested in doing stuff with the parameter mu. So how do we estimate it? Sample mean. That's the maximum I can estimate, which produce and T is 108. So on average, 108 hours these air conditioners last. EDF, QQ plot. Please make sure that you see how I do this on your own. And this just kind of reproduces the plot that we saw in the notes. Okay. So to make sure that this is clear then, y is distributed f, which is exponential mu. So then y star will be distributed exponential y bar. What else do we need here? T is going to be y bar. Expected value of T star given f hat is y bar. Now, note that y bar, or T, has in it a sum of exponentials. Now you know from, again, Cassell and Berger, set 882-83, the sum of independent exponentials is gamma. In our book, so we're going to have to do a lot with gamma distributions here. And unfortunately, our book has a weird parameterization of the gamma. I had never seen this before until I was first reading the book. And up here is the book's parameterization, and down below is the old Cassell and Berger parameterization. And essentially, what's going on here is that, let's see, beta is equal to mu divided by kappa, and alpha is kappa. Now, why does our book do that? Well, they want expected value of y to be mu. That's why. Just a reparameterization. So what that means then for us, using the basics of what you would learn in 882, the sum of the y's is now in our book's notation. Gamma, with its first parameter being n, the second parameter being n mu, the sum of the y's. then y bar, or t, would be gamma n mu. So t star then would be gamma n mu hat. We have the exact distribution. Great. But then there's other situations, of course, that you don't just want to work with, let's say, mu itself, or t. Instead, what you might want is, for example, 1 over mu. Well, what are you going to do? Well, find the distribution of t over 1 over y bar. One could show that's what's called an inverted gamma distribution. T star would also be inverted gamma with appropriate changes to the parameters. Well, what about log of y bar? Well, guess what? That's not a named distribution. So what are you going to do? Well, again, you can apply stuff that you learned in 882 to do a transformation and find the exact distribution of t. We'll actually do that later in the course. But instead, what you might want to do, if you saw something like that, is, well, why don't we just use the asymptotic distribution? Y bar has a large sample normal distribution, so you should be able to figure out what log of y bar is as well. You could do that. Instead, again, as we discussed before, why don't you just take resamples from f hat, calculate t every single time, and there you go. Okay. So how can we take resamples? Well, one way would be to use as, well, what function do you think in R is going to give us the resamples for an exponential distribution? R exp. That's what it ends up being. I'm going to show you now a different way that you can do the resamples. So if you page ahead, and the reason why I'm doing this is so that this will help you out in the project. Page ahead to page 234. So again, what you could do, if you wanted to take, let's say, 1,000 resamples, again, you can say R exp n equal 1,000 times the sample size n, which was 12, and then rate equal, that's just the name of the parameter, would be 1 over the mean of y. That's how you could take your resamples. Alternatively, you can use what's called the boot function. This is in the boot package itself. So I'm kind of skipping around here. We mentioned that you first need to say, I want to do stuff with the boot package. So I say library boot. Boot functions, the boot package is automatically already installed and on. You don't need to download it. And the function that we want for the boot package, well, guess what? It just happens to be exactly the same name, boot. So first thing I'm going to do is set a seed. The reason being is I want to be able to reproduce my results later. Say boot. My data is in Y. Let me make sure I get my data in Y here. So, there's Y. My statistic of interest. This is what I want to calculate every single time. I have written a function called mean.t. Since this is such a simple thing that we want, I want to find the mean every single time. I could just simply put mean, use the actual mean function R. Instead, to illustrate this more, I wrote my own function, mean.t. Function, I'm going to pass in data. See that? And I'm going to calculate mean of t. So just to verify that indeed that this works, I can say mean.t data equal y. Oh, I guess I already had that. Sorry. 108. Number of hours. Suppose I want 1,000 resamples. If I want a parametric bootstrap, I need to say sim, or simulation, equal parametric. And then I need to say, well, how are you going to actually take the resamples or simulate the data? And this is where you need to specify another function. And I decided to call it sim.data. Call it something else if I wanted to. And the function looks like this. The first argument has to be data. The second argument has to be MLE. It has to be called that. Kind of weird, but it has to be. Because often you're working with maximum likelihood estimates with distributions, so that's why the authors of this code have made that requirement. Then use REXP, random exponential. N equal length of the, is my sample size, or length of what's in data. And then there's that rate, 1 over the MLE. You could run this on your own, the sim.data, just to verify it worked. I'm not going to do that here due to time restrictions. And then you need to say, well, what is MLE? Well, mean of what? Now, you'll see examples later in the semester where you might have, let's say, two estimates that you need to pass into this function. And let's say instead I was sampling from a normal distribution. And I might want mu and sigma squared, or the corresponding estimates. Then in that particular case, you would need to use something like this, where you actually create a vector that contains all this stuff. You'll see examples later. I at least wanted to point that out now. First talk about this. I put all the results into boot.res, for lack of a better name, boot results. And then let's take a look at what's in boot.res. And here we go. What's produced by default is we have the following. Here's my original value of t. In other words, the mean of y. We have an estimate of bias. We have an estimate of standard error for t. We'll talk about that later. Remember, you can also do names, boot.res, to see further what's inside of it, because boot.res actually is a list. And you see a variety of things listed there. In particular, boot.res $T0 is the initial t. If I do head boot.res $T, there's T1 star, T2 star, T3 star, and so on. Other stuff here is rather self-explanatory. Boot.res $statistic. Here's how the statistic was calculated. Okay. I can also do plot, boot.res. Remember, plot is a generic function in R. And so that there is, let me show you. If I do class boot.res, guess what? It's a class of boot. So if I do methods class equal boot, you will see, for example, there's a plot.boot. So if I say plot boot.res, see what happens. We see the histogram, like what we've been doing before. The dashed line there is the observed value of t. You also always get, by default, a QQ plot. Notice that, what do you think about normality here? Maybe some problems? You remember what t is. It's a sample mean. Central limit theorem says that for a large sample, you're going to get a normal distribution. The sample size is 12 here. So this is an example then of a case where asymptotics is not going to work out for you as well as you would like it to. But the bootstrap, we could use this instead. Not necessarily worry about the problem. I'm not saying the bootstrap distribution is going to be perfect, but it often will provide a better approximation. Okay, so with that then, we have enough to at least start talking about the project so you can get going on it. Oh, I forgot to open it up. Let's see. Okay. For some reason, I got motivated by Cassell and Berger this semester. And so my theme for this particular project is for you to relive some of your days from Stat 882 and 883. I keep on going back to it, but that's why I say those courses are so important for what we do in our course here. And so Cassell and Berger actually do have some problems on the bootstrap. Problem 1 and problem 3 talk about the non-parametric bootstrap. Obviously, we haven't really touched on it too much yet, a little bit in chapter 1. You might be able to get started on it if you want to, or you can wait. It's up to you. Let's look at problem number 2. So, I have to admit that I didn't like the exact problems in Cassell and Berger, so I used those to motivate me here. You can look at the problems. That will help you out some. But it's not totally necessary to look at the problems. So this is based upon example 10.122 from Cassell and Berger. And there's a sample size of 9. And they actually say that this comes from a normal distribution. Okay? And we're going to be very interested in the sample variance t. Eventually, what I want to do is some inferences about t. In particular, I want to find a confidence interval for, I don't want to do inferences about t, I want to do inferences about sigma squared, excuse me. I'm going to use t to help me do that, and also the distribution of t to help me do that as well. So, to begin with here, well, why don't we examine the normality assumption for the statement. Now, you would expect that this should work out okay, but this is again how you would start a parametric bootstrap problem. I have this distribution. Let's look at the assumption. And also sample size of 9. Be careful. You're not going to expect it to be things to be perfect. Part B. If normality was correct, what are the probability distributions for y star, y bar star, t star? We've actually already kind of talked about that earlier today. I'll let you go back to the notes to find that. Also, what would be expected value star of t star, variance star of t star as well. Then part C, we're going to estimate the variance of t. So we're estimating the variance of a sample variance. Be careful there. And I want to estimate it using, basically by estimating var star of t star with the parametric bootstrap. 1999 resamples. Use the boot function. Use the normal distribution as well. Use a C number of 8712 so that everyone in our class will get exactly the same result. Construct a histogram of the t star values or related probability distribution of t star on it. And comment on the agreement or disagreement of the histogram and the probability distribution. So you know what the distribution of t star is. You should know that. In fact, it's actually in the notes, unfortunately. Didn't pay attention to that until after I had written up this project. Oh well. So things should agree. And so again, similar to what we've been doing, we're going to look at stuff that we know the actual distribution, and let's also look at the Monte Carlo estimate. Then to relive your STET 883 days, why don't you show me what the exact variance of t is? So I'll actually go through the derivations, not too difficult. Probably already done that before. And then estimate the variance of t using the max likely estimates of the parameter. So what do? See sigma squared in there? We'll replace with sigma hat squared. Then, finally, fill in the values for the table below. So just kind of summarize everything that we've done. So the actual value of the variance. Make sure. You should know what this is. And I failed to put that in there. Cassell and Berger actually do tell you what sigma squared is. If, for some reason, you decided to sell back your Cassell and Berger book, first, shame on you. But if you did, I can give you photocopies. Okay? Maximum likelihood estimate of t, variance of t, so basically part D. You know what that should be based upon the actual true distribution, and then through the resamples, you can calculate the estimate. Part F. Now what I want you to do is basically do this process of resampling for using 1,999 resamples, I want you to replicate that 1,000 times. So you're doing a lot of resampling here. Okay? So you're basically doing a Monte Carlo simulation of a Monte Carlo simulation. Well, why? Well, I think there's an error in Cancel inverter. And this will prove it to you that there is indeed an error. So what I want you to do is calculate basically this variance for every single 1,000 times. Construct a histogram of all these variances. And then comment on how likely it was for Cancel inverter to actually obtain a value of 4.33 for their estimate of basically this right here. They had 4.33. Then part G. Here's the old standard confidence interval that you probably learned in your first or second stat course for sigma squared. Discuss the assumptions that are used to derive this formula, and also calculate 95% confidence interval using the available data. Then later, this is section 2.5, we will learn about how to do a bootstrap version of a confidence interval. Okay? So that's problem number 2. You can at least get started on it if you want to over the weekend. You have nothing else to do. You're welcome to get started on 1 and 3, but we will talk about those in a little bit more detail in class once we do the non-parametric bootstrap. And as I said, this is due September 13th, provided that we can get through all that first part of Chapter 1 material. If for some reason we're not able to, then I will move back from the due date to make sure that you have enough time between when we finish the material to when the project is due. Okay. So I because I was worried about time here, I kind of went through number 2 faster than what I wanted to. If you do have questions over the weekend,